Have you ever gazed up at the night sky and wondered about the billions of stars out there? Picture this. Each twinkling light in the sky is a star, much like our own sun. And around many of these stars there might be planets, just like our Earth. These planets beyond our solar system are known as exoplanets. The study of these celestial bodies is not just about ticking off another box in the cosmic checklist. No, it's about understanding the grand tapestry of the universe. These exoplanets hold the key to unraveling mysteries of planetary formation, diversity, and the tantalizing potential for life beyond our solar system. Now you might be wondering, how do we even know about these distant worlds? The journey of discovery has been long and fascinating. It dates back to the early 1990s when the first exoplanet orbiting a sun-like star was spotted. A duo of Swiss astronomers, Michel Mayer and Didier Queloz, made this groundbreaking discovery, opening up a new frontier in space exploration. Since then, the quest to find exoplanets has gained momentum, with each discovery adding a new piece to the cosmic jigsaw puzzle. The Kepler Space Telescope, launched in the year 2009, has been instrumental in this journey, identifying over 2,000 exoplanets during its lifetime. And then there was the year 2018, a milestone in exoplanet research. That's when NASA's Transiting Exoplanet Survey satellite, or TESS, took up the baton from Kepler, embarking on a mission to survey the brightest stars close to our solar system. It's all about finding those hidden gems, those elusive exoplanets that could potentially harbor life. So we've established that space is vast, unfathomably so. And within this vastness, there are billions of stars, each potentially hosting its own planetary system. But with such a vast playground, how do we find these elusive exoplanets? Stay tuned as we delve into the intriguing methods scientists use to detect these distant worlds. So, with billions of stars to explore, how do we find these elusive exoplanets? Detecting these far-off worlds is no easy task, but scientists have developed a few ingenious methods. Let's start with the transit method. Imagine you're sitting outside enjoying a sunny afternoon when suddenly a bird flies across the sun. For a fleeting moment, the sun's brightness dips ever so slightly. This is essentially how the transit method works. Scientists observe distant stars and look for tiny dips in their brightness, which could indicate a planet passing in front of the star, much like our bird crossing the sun. This method is quite effective, but it does have its limitations. Next up is the radial velocity method. This method relies on the fact that a planet's gravity tugs on its star, causing the star to wobble slightly. By measuring this wobble, we can infer the presence of a planet. However, this method is best for detecting large planets close to their star, and it's harder to spot smaller planets or those in wider orbits. Thirdly, we have microlensing. This is a bit more complicated, but bear with me. According to Einstein's theory of general relativity, gravity can bend light. So, when a massive object like an exoplanet passes in front of a distant star, it bends the star's light and magnifies it, creating a brightening effect. This effect is called a microlensing event, and it can reveal the presence of an exoplanet. The downside? These events are rare and unpredictable, and once they occur, they can't be repeated. Lastly, there's direct imaging, essentially taking a picture of the exoplanet. As you can imagine, this is extremely difficult. It's like trying to see a tiny firefly buzzing around a dazzling searchlight from miles away. But with advanced telescopes and clever techniques to block out the star's blinding light, we've managed to directly image a handful of exoplanets. It's important to note that each method has its strengths and weaknesses, and often they are used in combination to confirm the detection of an exoplanet and to learn more about its properties. These methods are continuously being refined, and new ones are being developed. For instance, the field of astroseismology, the study of starquakes, is showing promise in detecting exoplanets. Scientists are also using AI and machine learning to sift through vast amounts of data and identify potential exoplanets. Though they are far away and often hidden in their star's glare, exoplanets are revealing themselves to us. The universe is full of mysteries, and as we perfect these methods, we're inching closer to unraveling some of its most tantalizing secrets. Just as our own solar system is diverse, so too are the exoplanets we've discovered. Now let's take a closer look at the diverse range of exoplanet properties. The size and mass of these celestial bodies are as varied as the stars in the sky. Some exoplanets, known as super-Earths, are just slightly larger than our own planet, but still smaller than the gas giants in our solar system. Then there are the behemoths, the gas giants, which dwarf our own Jupiter in size and mass. The composition of these exoplanets is equally intriguing. Some are rocky, much like Earth and Mars, while others are gas giants like Jupiter and Saturn. There are also ice giants, planets composed largely of substances with relatively high melting points, compared to hydrogen and helium, such as water, ammonia, and methane. Perhaps most fascinating are the water worlds, planets where the surface is entirely or almost entirely covered by an ocean of liquid water. Exoplanets also exhibit a wide array of orbital characteristics. Some orbit their stars in mere hours, while others take hundreds of Earth years to complete a single orbit. The distance from their host stars also varies greatly, which impacts their potential for habitable zones, regions where conditions might just be right for life as we know it. The atmospheric composition of these worlds is another area of fascination. Some exoplanets have atmospheres filled with water vapor, while others show signs of methane, carbon dioxide, or other gases. These atmospheric compositions, particularly the presence of water vapor, could serve as biosignatures, indirect signs of life on these distant planets. However, it's important to note that our understanding of these exoplanets is still limited. While we can infer a lot about their size, composition, and orbits, the internal structures and geological processes of these worlds remain largely a mystery. For instance, we don't yet know if these planets have tectonic activity like Earth, or what kind of weather patterns might exist on a gas giant exoplanet. And yet, despite these challenges, we continue to learn more about these distant worlds every day. Each new discovery brings us one step closer to understanding the diversity of the universe and our place within it. In the grand scheme of things, it is quite humbling to realize that our Earth is just one small planet among billions, perhaps even trillions of others. Each exoplanet we discover is a reminder of the vastness of the cosmos and the endless possibilities it holds. Every exoplanet is like a puzzle piece, helping us to piece together a broader picture of the universe. By studying these diverse worlds, we're not only learning about the universe, but also about the potential for life beyond our own planet. It's a thrilling time to be involved in exoplanet research. With each new discovery, we're pushing the boundaries of our knowledge and understanding and opening up new frontiers for exploration. So as we continue our journey through the cosmos, let's remember to keep our minds open to the infinite possibilities that lie ahead. The universe is a vast and diverse place, and we're just beginning to scratch the surface of what's out there. Each exoplanet is a new world with its own unique story to tell. As we continue to refine our detection methods and technology, the future of exoplanet research looks promising. The next generation of telescopes and missions are on the horizon, ready to propel our understanding of these distant worlds to new heights. Imagine a telescope so powerful it can capture the faint light of an exoplanet billions of miles away. That's precisely what the James Webb Space Telescope, or JWST, is designed to do. Set to be the most powerful space telescope ever built, it's poised to revolutionize our understanding of exoplanets. It's able to detect and analyze the faint light of exoplanets, allowing us to discern their composition, climate, and even the potential presence of life. But the JWST isn't alone in this quest. The Planetary Transits and Oscillations of Stars, or PLATO, is another mission on the cards. It's designed to find and study a large number of extrasolar planetary systems, with a particular emphasis on the properties of terrestrial planets in the habitable zone around solar-like stars. These missions, and others like them, will help us characterize exoplanets in greater detail than ever before. They'll enable us to paint a more vivid picture of these alien worlds and perhaps discover something truly astonishing: evidence of life beyond Earth. The search for potentially habitable exoplanets is one of the most exciting frontiers in astronomy. Every new exoplanet we discover brings a fresh possibility. Could this be a world where life as we know it could thrive? Could it be home to a form of life utterly different from anything we've ever imagined? These aren't just questions for science fiction anymore. They're questions that science is actively striving to answer. And as our technology advances, so too does our ability to answer these questions. Techniques like spectroscopy, which analyzes the light from a star to determine the composition of an exoplanet's atmosphere, could potentially reveal the presence of biosignatures, telltale signs of life. But why stop at remote observation? What about actually going there? While interstellar travel may still be a concept relegated to the realm of science fiction, it's a dream that scientists and engineers are actively working towards. There are ongoing projects aimed at reaching Alpha Centauri, the closest star system to us, which is thought to have potentially habitable planets. One such project is Breakthrough Starshot, an ambitious initiative that plans to send a fleet of tiny, light-propelled spacecraft on a 20-year journey to Alpha Centauri. If successful, it would mark the first time that human-made objects have left our own solar system to explore another. Imagine that, not just observing these distant worlds from afar, but actually visiting them. It's a thrilling prospect, one that could redefine our understanding of our place in the cosmos. So as we gaze into the night sky, we can dream of the possibilities that lie within those distant points of light. Each one could be a world much like our own, or something entirely different. Each one holds the potential for new discoveries, new insights, and perhaps new life. The journey to these distant worlds is just beginning. The study of exoplanets has come a long way, but we still have much to learn. In the grand cosmic scale, our understanding of these distant worlds is just beginning. We've learned about the rich diversity of exoplanets, from super-Earths to gas giants, and the myriad of compositions they can hold. Rocky planets, gas giants, ice giants, and even water worlds have been discovered, each with their unique orbital characteristics and atmospheric compositions. These exoplanets, in their wide-ranging diversity, present an exciting possibility, the potential for harboring life. With each new discovery, we edge closer to answering the age-old question: are we alone in the universe? Or could there be a distant world where life as we know it, or perhaps as we don't know it, thrives? The study of exoplanets is more than just a quest for alien life. It's a journey into understanding the universe and our place within it. Every exoplanet discovered, every star system studied, enlightens us about the processes of planetary formation and the dynamics of celestial bodies. Yet with all we've learned, there are still many questions left unanswered. We've barely scratched the surface of understanding the internal structures and geological processes on these exoplanets. The limits of our current technology challenge us, but they also inspire us to push the boundaries, to develop new methods, and to build better tools for exploration. Looking ahead, the future of exoplanet research is bright. With already launched new generation of telescopes and missions like JWST and PLATO, we'll get to characterize these exoplanets in even greater detail. Interstellar travel, once a concept restricted to science fiction, is now a real possibility being explored. Each step we take in this direction brings us closer to the potential for direct exploration of these fascinating worlds. As we continue to explore the cosmos, who knows what new worlds we'll uncover next?